Okay, I've been talking a lot about machine code and how assembly language is too high level. I've written a blog about how to do straight machine code, whether you're using an assembler like NASM, or I even wrote a script that allows you to type just straight machine code and it'll wrap it all up for you to execute. But still, reading a blog entry may not make it real enough. You might not really get why you'd want to do machine code or be motivated enough to try it. And I mean, well, maybe it's not motivating, but to me, it's interesting. So an old friend of mine, a really good friend of mine, wanted to see a video of how this is done from start to finish with the script that I wrote. So that's what this video is going to be about. I'm going to go over a really, really simple program. And we'll be using the Intel manual to base all the code off of for our machine code. What it's going to do, what I'm going to try to do is I'm going to XOR two 8-bit registers, and that's it. But I mean, first, before you XOR data from registers, you need to get data into those registers. So that's where we'll start, is with the move command that we see up here on the Intel manual. And this is volume 2. Volume 2 of the 3 volumes of the Intel manual is where it has all the instructions and how they're encoded. It's my personal favorite volume of the Intel manual. And I've read them all, and yeah, I know it's a page turner with 3,500 pages here. Uh, so, being that we're dealing with 8-bit values, and just like hand-coded specific ones, we're going to be dealing with this B0 range of opcodes for this instruction. So this is the assembly side over here. It means move an immediate hand-coded 8-bit value into an 8-bit register. And I know it looks like it's kind of going in reverse, but really assignments and even high-level languages kind of go in that order, where you say, you know, I want this variable to equal this value. It's kind of straightforward. So this machine code part of it, though, the B is probably the part that specifies move. This 0 isn't actually to be taken literally. It's what really specifies the register we want to use. So 0 would be like our AH register or AL register. If it was a 1, it would be the CL. If it's 2, it would be DL, 3, BL. And I know I'm not counting in alphabetical order here, but that's just the order it goes. And then if you go all the way past 7 and get into B8, this is where you're dealing with another 8 32-bit registers. But we'll do the B0 version of it. So I'm going to go over to my Linux Mint VM here and start typing some machine code. So we got our B0, which is the AL register, and we're going to be moving 5.5 into it. And also with this, you can do comments. So the equivalent assembly would look something like that, but I don't need to have that in there. I'm just putting that in there for an aid. And also I'm going to move value into ECX, which the only reason I choose ECX is it's just the next, B0, B1. I'm going to move AA into there. And I'll put a comment here just so it looks nice. And the reason I chose those two values is, like, if we look at a 5 in binary, we have that. If we look at an A in binary, we have that going on. So it's cool if you XOR it, it's just going to be straight like that. So the result would be FF, and I kind of like that. So the next thing we need to do is we need to XOR those two registers with each other. So I go down to that command or instruction in the manual, kind of near the end here. So I want to XOR two 8-bit registers. There's a couple options we can do for that. The first option that an assembler would pick is this 3.0 machine code here. The format for that is XOR, and then the first operand can be, what this means is either a register or a memory location or a pointer. And then the second operand has to be a register. A similar version is this 3.2 down here, but the difference is the first operand has to be a register, whereas the second one can be either or a register or a memory location. So the interesting thing to me is that for both of these, you can encode both operands as just a register. It's kind of a redundancy, and we'll explore that too. So let's go, remembering that we're using our 3.0, we'll go over here and do the 3.0 part of it. And then, how do we say, I want AL with CL? We can't do that. We're doing machine code. So how do we encode that? So that's where we go up to our mod_rm encoding section, which is here in the manual. And you get a little table like this. It's an 8-bit value, but it's broken up by 3 separate little areas the mod and the R or RM and then another R or RM. So in this case, we're doing registers, not crazy offsets or any stuff like that. So when you're doing just two registers, the mod is a 1-1, and that's in our area here. So I'm just going to start as a scratch pad typing out that part as a 1-1. Next, we're going to be doing AL. So let's go over and find that. Although they're actually, the order of them are switched, so I'm going to put the CL apart first. So our CL, if you look here, CL is our value that we want to do. That would be an 01 or 001. So we'll put that in there. And then we want an AL, so that's that part up here, and that's just 000. So we'll put that there. And if you go down here to like kind of cheat and give you that this is going to be C8, yeah, so I'll go over and I'm going to type C8 up here. But if you didn't have that little table and you remember that the mod for registers is a 1-1 and you know the order of the registers, because it really is the same thing we're talking about with our moves, the A register, the C, the D, and the B. It's the same thing here, A, C, D, B, same order. So if you wanted to hand do it, that helps me visualize it a little bit more. I know that that binary is a C, and I know that binary over there is an 8, and we get our C8 up there. And that's how that works. So it's a lot of stuff, but really that's just XOR ALCL. And I'll put that in our comments here. And then this last part I don't really have to put, but it makes it a little bit nicer. I want, being that we're in Linux, I want the program to actually finish nicely. There's actually an exit API call to the Linux kernel. To do an interrupt to the Linux kernel, it would be, for most of the interrupts, it's interrupt 80 is what they call it. And that interrupt opcode is CD, and then 80 would be the value. But for Linux to know what you want to do, like which actually API you want to do, you have to specify that in the EAX register. So there's a lot of different values you can do for that. I mean, you can do a lot of things like input, output, whatever. But we're just going to exit. And to exit, you want to have the number 1 loaded in the EAX register before you do the interrupt 80. So we'll just use that B0 move command again and just throw 1 in there. And I'll do this thing here so it looks nice. And we'll do the int 80 or whatever, you know. And I'm going to go ahead and save this. This is our machine code, and I'll make it executable. So I'll call my script. And the input file is going to be machine.m. And the output, I'll just make machine. And it's in there. And what it's really, well, actually, just to show what it's made up of here. You notice there's a lot more stuff than what we just typed. But let's start at the B055, if we find that there. This is pretty much our program. We do see it in there, like literally how we typed it. But what's all this other stuff? Well, that's what my script does for us to make things easy. I mean, it's not like the old days with DOS COM files where you could actually literally just have just executable. But with Windows PE files and Linux ELF files, you do have to have a loader that tells Linux to actually load the machine code. So what it's really doing for us is this whole kind of ELF format here. You know, it just adds all the metadata that we need. You know, it's kind of useful. And also another cool little thing it does for us is we normally by default your programs are readable and executable but not writable. Well, the m2elf script can make it writable as well, so you can have self-modifying code, which is usually a big no-no, but it's fun for learning purposes. So that's our program. Let's look at it in a debugger, because if we were just to run it, oh wait, it's not read, write, execute. The new version of the script on GitHub does this part for you, but it's no biggie. We'll just do it right now. There we go. So now I can run it. And it doesn't do anything. It also doesn't error out because we did that interrupt 80 thing to exit correctly. So now load up EDB so we can see the XOR in action. All right, so you'll notice all this commenting I did over here, just to be nice. Well, it's pretty consistent what the debugger disassembled right here. Although I did say 5.5 and it says 8.5 there. Well, you do see our machine code still says 5.5. This 8.5 is actually a decimal representation of 5.5, so no biggie. So I'm going to step through this one instruction at a time. I'm stepping right now, and in the RAX or EAX, or it just depends on context, but really this last byte here is the AL register. So you see that 5.5 loaded in there. And I'll step another time, and now we see AA loaded in our C register, and then we'll XOR it. So let's see, the A register should have the FF when we're done XORing, and there it is, the FF. And then we're going to move 1 back into that register, so then we can do the int 80, and it executes, exits fine. So that was writing machine code, straight hex, without assembly. And there, like I was saying, if you really want to see why this is really relevant, because I didn't really show the cool tricks you can do with machine code that can't be done in assembly. There are some videos I think that I have up, but really if you check out my blog at xlogicx.net, a lot of posts go over a lot of really weird tricks where you can do things only in this area that you can't do in this area here. It's really neat. So any of the blog entries that start with the phrase assembly is too high level, that's where you want to look for some of those really weird tricks. I hope this made things clear on how to jump in and do this yourself. If it sounds too complicated to go grab the Perl script from GitHub, I mean, which isn't really that complicated, but I mean, also you're going to want the rest of the stack like EDB and all that stuff if you want to see it in a debugger. You should be able to get Kali Linux or even Remnix. Either one of those will have a lot of the stuff like EDB and all that. Remnix specifically, though, and it's spelled REMNUX, it actually comes prepackaged with my m2elf tool. So everything would be out of the box. Everything you need that I did here will be out of the box with the Remnix VM.